students, coming to the next example for the shortest path distance. In the previous first shortest path problem that is divided into two types, which solves the single source shortest path, that is the Dijkstra algorithm and Bellman-Ford algorithm. In the previous video I explained about the Dijkstra algorithm. Now let us see the Bellman-Ford algorithm. So actually this algorithm also solves the single source shortest path problem of directed graph. So this is a directed graph, whereas here Dijkstra is also a directed graph, but the only difference here is G is V comma E. So here, in which the edges weight, so whatever the weight that edges is having, those weights may be negative. So in Bellman-Ford, you can this can accept the negative weights, whereas in Dijkstra algorithm only the non-negative weight should be accepted by the edges. But in Bellman-Ford's you can take the negative values also. But moreover, if you are taking the negative, moreover, this algorithm can be applied to find the shortest path if there does not exist any negative weighted cycle, So it can also be considered that it can take the non-negative values also, and it does not exist that negative weighted cycles. Negative values can be accepted, but negative weighted cycle cannot be accepted in Bellman-Ford algorithm. So let me write the algorithm for this Bellman-Ford. Here I am writing algorithm Bellman-Ford algorithm GWS. So just like Dijkstra, for each S is the starting vertex, G is the graph, and W is the weight vertex. V belongs to G dot V. So now check V dot D, the destination should be infinity, and V dot pi, the starting should be, make it as a nil, and S dot D should be 0, start with a 0. For I is equal to 1 to mod G dot V minus 1. For each edge U comma V belongs to graph dot G dot edges. And condition, if V dot V, same just like Dijkstra, V dot D is greater than U dot D plus W of U comma V, V dot D, then you make it V dot D is equal to U dot D plus W of U comma V, and V dot pi should be U. So up to here it is same for the Dijkstra algorithm. So after that you have to check for each edge U comma V belongs to G dot E if V dot D is greater than U dot D plus W of U comma V. You have to return false, else return true. So this is the algorithm for the Bellman-Ford. Now let us see the example for this. So here is an example for the Bellman-Ford algorithm. So the starting, this is I have taken the graph. So this graph has negative edges also. Do you observe here? This is the negative edges also this graph consisting of. This graph has negative edges but does not have any negative cycles. You don't have negative cycles. Only negative edges are there, but it doesn't have any negative cycles. So cycle means the complete connected graph, closed graph you call it. So hence the problem can be solved using this Bellman-Ford. So this graph can helpful to solve the Bellman-Ford algorithm. So first you have to check whatever the graph that they are given is ready to solve the Bellman-Ford algorithm or not. So first see whether the negative values are there. If negative values are there, no problem. The Bellman-Ford algorithm will solve that negative values also. But you have to consider there should not be negative cycles. So at the time of initialization, all vertices except the source are marked by infinity. So here except the source, all the remaining vertices are marked infinity. Okay, and the source should be marked as 0. This is the source and this is the destination. S is the source and D is the destination here. Okay, and here the vertices names A, B, C, D, E, F. So this is the F, G, H. So these are the vertices and the vertices values, the weighted graph. So coming to the first. In the first step, all the vertices, so whatever the vertices, all the vertices which are reachable from source to destination, the source are updated by minimum cost. So let me explain once again. In the first step, all the vertices which are reachable from, so this vertex is reachable from this vertex, source vertex, and this vertex is reachable from source vertex. So these two vertices are reachable. So that's why the vertices which are reachable from source vertex are updated by minimum cost. So we have to update it with the minimum cost. Hence A and H are updated with what values? So 0 plus 5. Okay, 0 plus 5. So they mark it as a 5. And this is 0 plus 2. I mark it as 2. Okay, so now coming to the next. In the next step, so here in the next step, vertices A, B, F, E. So already A, H is updated. Next, the vertices that are reaching from the A or B, F. Okay, and you have to take the E also because from H it reaching E. So all these three vertices. So from A, the reaching vertices are from, this is a source here, the reaching vertices are F and B, and from H the reaching vertices is E. So these three has to be updated. So update A, B, F and E. So with what values we have to be updated? So here the arrow is coming like this. So first you check this 2. So here the 2 is there. And this is coming this side, so don't care this. So now check here, 2 plus 2. Okay, 2 plus 2 becomes 4. So but here this is 5. So just overwrite that and mark it as a 4 and add 4 plus 3. You will get 8. That is coming here. So 8. And now check. So E has to be updated with what value? 2 plus 9. 2 plus 9 is equal to 11. Okay, this satisfied. Okay, and here check. So this arrow is coming from like this. So up to here we updated. Now coming to the next step. So in the next step, following the same logic in these steps, vertices B, F, C, and G has to be updated. Vertices B, F, C and G are updated. So with what values we have to be updated? So now check. So from B, 4 plus 7. 4 plus 7 is 9. No, it is sorry, this is going from this, right? Okay, so but 4 plus 7, now check here, 7 plus 2, 7 plus 2 becomes 9. Okay, this is satisfied. 7 plus 2, 9 is satisfied. Now check this side. 7 plus 6, 7 plus 6, so F. So this is not satisfied here. Okay, so 7 plus 6, it is not reaching to, it's becoming 13, so this is not satisfied. Now check here, 2 plus 9, so 2 plus 9, okay, we get the 11, so this path is okay. Okay, so this is 0 plus 2 is okay, and 2 plus 9 is okay. Okay, and coming to here, 7 plus 2 is 9, okay, and 4 plus 3, 7, so this path is also okay. And now check here, I have to update C also. 9 plus 8, 9 plus 8, I'm getting 17. Okay, this 9 plus, so first we have to check this. So this is a G. So G is come from 11 plus 2, this path 13. So first, don't be confused. So first you have to check one path. Afterwards you check the other paths. If that path is not satisfying, you just discard that path. Okay. So here 11 plus 2 is 13. Okay, this is satisfied. Now I'm checking this 13 plus 3. No, you want the value, it has to be 16. So now in the last, hence here the C and D vertices are updated with the new values. So now check here. So I mark it whatever the value, 9 plus 8. No, this 13 plus 3 is 16. This is satisfied. 11 plus 2, this is 13. This is satisfied. Okay, and the same way now I'm coming this path, 0 plus 2 satisfied, 2 plus 9, 11 satisfied. So this is the one path. And next 16 plus 4, 20. So this is the path which satisfying the conditions. Okay, so hence the minimum distance between vertex S and D is 20. Okay, so the minimum distance it is from S and D is 20. So based on predecessor information, the path is S to H, H to E, E to G, G to C, and C to D. So this is the path. So here a little bit confused, but the final we have to be choose the route which is having the shortest distance. That should be a single shortest path. Single source shortest path we have to be find out. That is a Bellman algorithm. Thank you.